welcome back to my YouTube channel. So today in this video we'll be discussing one derivation, and the topic of the derivation is refraction at curved spherical surface. So this is from the chapter Ray Optics for class 12. Alright, so let's do this derivation. So I have drawn this diagram. You can see the diagram. Let me explain this diagram and then I'll explain the terms and we'll do the derivation. So this same question can be also asked mentioning the relation between U, V, R, N1 and N2. Okay. So here in this diagram you can see we have a curved spherical surface, and the surface here is convex surface. You can see this. So curved spherical surface. This is a denser medium which has refractive index N2, and outside we have rarer medium whose refractive index is N1. So this is the line passing through the center, which we have written as the point M here. Now we have an object O outside this curved surface. Now from the object we are taking two incident rays. One which is passing through the center goes without any deviation in the same straight line, and the other is going in this direction. So these are the two incident rays. This one going to the center without any deviation, and this one going in this direction. Now at this point, which is point N, we will drop a perpendicular or normal to this surface, and this normal will pass through the center of curvature C. So this angle between the normal and the incident ray, this angle is our angle of incidence I. Now as the ray of light goes from the rarer medium towards the denser medium, it will bend or it will come towards the normal. So after this point N, the ray will move in this direction. That means it will bend towards the normal, and the two refracted rays will intersect at this particular point where we get the image of this object. So this angle here is the angle between the normal and the refracted ray, which is called as angle of refraction. And we have taken three other angles. This angle is alpha, this angle is beta here, and this angle is gamma. Alright. Now the distance between the center and the object is called as the object distance. Center of this curved spherical surface and this object, this distance is your object distance. Distance between the center and the image, we call it as the image distance, which is represented by V. And from the center up to the center of curvature, this distance is our radius of curvature. So here you can see the terms. U represents your object distance, V represents your image distance, R represents your radius of curvature, N1 is the refractive index of the rarer medium, N2 is the refractive index of this denser medium, I is our angle of incidence, R is our angle of refraction. So after that, what we have done is we have dropped a perpendicular from point N on this principal axis, which intersects at the point P. So this line you can see in the red, NP, this is the perpendicular on the principal axis. So these are some of the terms related with this diagram. So let's do the derivation now. I hope the diagram is clear to you and the terms are understood. Let's do the derivation now. So if you take this triangle NOC, so we are taking the triangle NOC. So in this triangle, if you use the theorem for exterior angle and interior opposite angles, which says that exterior angle is always equal to the sum of interior opposite angles. So in this triangle NOC, this angle I is the exterior angle. This angle is outside, so this angle is exterior angle, and these two angles, that is alpha and gamma, these are the interior opposite angles. So using the theorem for exterior and interior angles, we can write I is equals to alpha plus gamma. So let this be equation number 1. Here we have used this theorem which says exterior angle will be equal to the sum of interior opposite angles. So this is the theorem which you have to remember here. So in this triangle NOC, so NOC here, this one is the exterior angle and these two are the interior opposite angles. Therefore we have written using this theorem exterior angle I equals to sum of interior opposite angles, which are alpha and gamma. So similarly, if you take another triangle, which triangle we are going to take? We are going to take NIC. So in triangle NIC, you can see that gamma is our exterior angle So we will use the same theorem again. So gamma will be equal to R plus beta here. So in this triangle, gamma is our exterior angle, R and beta, these are the two interior opposite angles. So using this same theorem, exterior angle gamma is equals to sum of interior opposite angles, which is R and beta. So be careful with the symbol for R and gamma, they look similar. So gamma and R, you write it properly. Now if you take beta to the other side, we will get gamma minus beta is equals to R, which can also be written as R is equals to gamma minus beta. So let this be equation number 2. So here you can see we have obtained two equations. I is equals to alpha plus gamma, that is equation 1, and R is equals to gamma minus beta, this is our equation number 2. Now for small angles, we can write alpha nearly equal to tan of alpha, and tan, we know that it is turned permanently black. So perpendicular base by base is our tan. So we need to find the value of tan of alpha. So for that, we will use this triangle NOP. So here we have the angle alpha. So if you take tan of alpha, then tan is turned permanently black. So perpendicular, which is our NP, and base, which is our OP here. So tan alpha will be from this triangle NOP, NP divided by OP, which is perpendicular by base. Now here we can do slight change. OP can be written nearly equal to OM here. So what we have done here, so in order to find the value of tan of alpha, we have used, if you have not understood, we have used triangle NOP. So in triangle NOP, if you take tan of alpha, which is turned permanently black, perpendicular by base, so perpendicular in this case is our NP and base is our OP. Now since P and M, they are very close to each other, so we can consider that OP is nearly equal to OM. So we can write this as this. Alright, so this is our equation number 3. Similarly, we can find the value of tan of beta and tan of gamma also. So beta can be written nearly equal to tan of beta for small angles. Similarly, tan beta will be perpendicular by base. So for this, we will take the triangle NIP. So in this triangle NIP, perpendicular is NP and base is PI or IP. So similarly, we can write NP, which is the perpendicular, and the base is PI. Now again, since P and M are close to each other, PI can be written nearly equal to MI. So this equation can be written as NP divided by MI. Let this be equation number 4. So for this we have taken the triangle NIP. So in this triangle NIP, tan of beta will give us perpendicular by base. So perpendicular here is NP and base here is PI. Now as I said, since M and P are close to each other, we can consider PI nearly equal to MI. So that's how we got equation number 4. Now we need to find the value of tan of gamma. So for that again, we will write gamma nearly equal to tan of gamma equals to, so for this we'll take the triangle NCP. So if you take the triangle NCP, again NP is your perpendicular and PC is your base. Now since P and M are close to each other, we can write this as NP divided by MC. Let this be equation number 5. So for this, which triangle we have taken? In triangle NCP, we have taken tan of gamma, which is perpendicular by base. Perpendicular here is NP and base here is your PC. Now since P and M are close to each other, we can write this as MC. So these are the equations that we have obtained. So alpha nearly equal to tan alpha for small angles, beta nearly equal to tan beta, and gamma nearly equal to tan gamma. So we will consider the triangles NOP, NIP and NCP. We will get the value of tan of alpha, tan of beta and tan of gamma. So one thing we have noted down here is, since M and P are close to each other, we have taken the distances OP nearly equal to OM, PI nearly equal to MI and PC nearly equal to MC. So similarly, for small angles, we can also write, from Snell's law we get N1 sine I is equals to N2 sine of R. So this is Snell's law. For small angles, we can write down sine of I can be written nearly equal to I and sine of R can be written nearly equal to R. So we are considering for small angles sine I nearly equal to I, sine R nearly equal to R. Now if you look at the equations, we have the value for I and R. From equation number 1 and equation number 2, we can put this value here. So let's do that. So we will have N1 times, look at the value of I is alpha plus gamma. Similarly, N2 R is our gamma minus beta. So here we have used which equations? We have used equation number 1 and 2. So from equation number 1 and 2, we have replaced the value of I as alpha plus gamma, this one, and R as gamma minus beta, this one. Now again, if we look at the equations, we have the value for alpha, beta and gamma in equation number 3, 4 and 5. So we can replace the values of alpha, beta and gamma here. So let's do that. N1 times alpha is our NP by OM from equation number 3. Gamma similarly is our NP divided by MC equals to N2 times gamma is NP by MC minus beta is NP by MI. So we have done nothing but simply replace the values of alpha, beta and gamma using equation 3, 4 and 5 here. So if you look at the equation, what we have done, we have obtained the value of alpha, beta, gamma. After that, we have used Snell's law, and for Snell's law, we have taken small angles, sine I equals to I, sine R equals to R. We replace the value of I and R from equation 1 and 2. After that, we get this one, and then we put the value of alpha, beta and gamma from equation number 3, 4 and 5. Okay, I hope you are understanding this much. Now let's take out the common from here. We can write down NP into N1 times 1 divided by OM plus 1 divided by MC. Similarly, from the right hand side, we can take out NP common into N2 times 1 divided by MC minus 1 divided by MI. Alright, so you can cancel this because we have the product. So NP gets cancelled. Now open the bracket on the left hand side with N1, on the right hand side with N2. So we can write this equation as N1 divided by OM plus N1 divided by MC. On the right hand side we'll get N2 divided by MC minus N2 divided by MI. So what we have done, we have just opened the bracket on the left hand side with N1, on the right hand side with N2. Alright, so after this what we will do is, you can see here we have MC and here we have MC. So we'll keep the similar terms together. So let's bring this to the left hand side and we'll take this to the right hand side. So continuation. So this we can write it as N1 divided by OM, minus comes to the left hand side, it becomes plus. This is N2. So N2 divided by MI is equals to, we have N2 divided by MC. This goes to the right hand side, it becomes minus N1 divided by MC. Okay, or what we can do is N1 divided by OM plus N2 divided by Mi is equals to, you can write this as N2 minus N1 divided by MC. Let this be equation number 6. So here we have obtained this equation, N1 by Om plus N2 by Mi equals to N2 minus N1 divided by MC. Now let's find out the value of Om, Mi and MC from the diagram. Alright, so from the diagram you can see Om, Mi and we need MC. So from the diagram you can see that the value of Om is nothing but U. So we have U here. The value of Mi is our V and the value of MC is our R. So from the diagram we get the value of Om, Mi and MC. But here you also have to be careful with the sign convention. I hope you know the rules for sign convention. For object distance from the center of this curved surface, we have to go towards the left. So when we go towards the left or in the opposite direction of the ray of light, then the sign will be negative. For V and R, we have to go towards the right. That means along the same direction as the incident ray or the ray in which it is traveling. So the sign convention for V and R will be positive. So you have to take care of the sign convention. Now you can put this value along with the sign convention in equation number 6. So you can write down putting in equation 6. So what do we get? Let's put the value here. We have N1 divided by Om. Om is our minus U. Then we have this plus. We have N2 divided by Mi. Mi is plus V, so V equals to, we have N2 minus N1 divided by MC, which is R. So we'll get minus N1 by U plus N2 by V equals to N2 minus N1 divided by R, or you can write this first, so it becomes N2 divided by V minus N1 divided by U, which equals to N2 minus N1 divided by R. And this is the required relation between U, V, R, N1 and N2, where U stands for your object distance, V stands for your image distance, R stands for your radius of curvature, N1 and N2 are the refractive indices of the rarer medium and the denser medium respectively. So this equation or this derivation is very important for class 12. You may get the derivation, alright, and also you may get numericals from here. So I hope you have understood this derivation. I'll be doing more derivations in the next video. So please do go visit the derivation and do comment, like, share and subscribe. Thank you everyone.